Welcome to an ultralight airplane design video from the Ultralight Airplane Workshop. My name is Leon. In this video we're going to look at the characteristics that we need for the airfoil on a horizontal tail of an ultralight airplane. In particular, we are looking at one for the UWS-1 Ultralight airplane that we're currently designing. And by the end of this video, maybe we'll even have one selected. Before we get to it, I'd like to thank Keith F. for becoming a patron of the Ultralight Airplane Workshop channel by becoming a patron on Patreon. If you'd like to support the channel too, you can click on the link down in the description for Patreon and then select the kind of tier you'd like to use to support the channel. Now let's get to it. Let's talk about an airfoil for a horizontal tail. Well, for you guys who really don't like looking at slides during these design videos, you'll be happy to know that we're not going to be looking at as many on this one, just a few. Mostly we're going to be looking at the XFLR5 program as I'm going through looking at some various options for an airfoil for our tail. I will be using a lot of aerodynamic terms in this video. What I try to do when I first use an aerodynamic term in one of these videos, I put a little box up in the upper right hand corner of the screen that is a link to an aero terminology video that'll describe the term. But YouTube only gives me 5 of those, and there are certainly more than 5 terms I'll be using in this video. So if I ever use a term and you don't see a link up in the upper right hand corner that talks about it, at the end of the video you'll find a box that is a link to the playlist for the aerodynamic terms. And you click that, and in that playlist you should find a description for the term. If I use a term that you don't find a video about, make sure you leave a comment down in the comment section for the video and tell me what I forgot to make an aero terminology video about. What are some of the characteristics that we want to use in determining the airfoil to use for our horizontal tail on the ultralight? Well, one of them we definitely want to meet is to make sure we can get this 0.9 coefficient of lift when we are near our stall speed. And if you'll remember, this 0.9 coefficient lift comes from the previous design video when we were figuring out the surface area for the tail. Now it's really not much of a challenge. Just about any airfoil can reach a coefficient lift of 0.9. So it's not as much of a concern, but we'll check just to make sure. Now something that comes into the structural part of it, not really so much the aerodynamic part of it, but I want the horizontal tail to be cantilever like the main wing is. And in order to do that, it's going to have to be fairly thick so we can put a spar in it so it can carry the aerodynamic loads that we're going to be having. We want to choose an airfoil that'll give us an elevator shape or chord that'll make the elevator effective. And then there are some stall characteristics we want to look at for this airfoil. We want to make sure the main wing will stall before the horizontal tail will. For most of the analysis we're going to be doing in this video, I'm going to be using a piece of software called XFLR5, and the version I'm using is 6.45. If you're interested in looking at this software, I've got a link down in the description fairly low down that you can click on and go to the website for them. Well, I thought a good way to start would be looking at some airfoils that are commonly used on airplanes and ultralight airplanes and kind of compare those and see what we can learn. Now one of them would be an airfoil like on the Minimax airplane. And that is basically a rounded edge about 1 1/4, 1.5 inches thick, and it comes straight back to the hinge, and then at the hinge it comes down in a fairly straight line, a triangular line, to a fairly sharp point. So we'll compare that one against something that's the tube and fabric kind of airfoil, and that's going to be something that in general will have a fairly large tube, and by large I mean something like 3/4 of an inch in diameter, maybe 5/8, back here near the hinge line. And then up near the edge, it could be 1/2 inch, 5/8 inch diameter steel tube. So it'll be fairly round up here and then quickly go to a straight line. Now, unfortunately, the XFLR5 program makes it so I have a little bit of a difficult time making it a straight line. It curves it just a little bit. And then you've also got some narrow tube on the trailing edge. In this case, I assumed it's something like a 1/4 inch diameter tube. And then another one that gets used on some of the larger airplanes, especially if it's got a cantilever airfoil, is going to be the NACA 009 airfoil. Now this is a turbulent airfoil, and that makes a lot of sense if your tail is going to be in the slipstream of a propeller. Doesn't make a whole lot of sense to have a laminar airfoil if you're in the slipstream, because you're not going to get laminar performance. So the 0009, of course, it's uncambered, it's symmetric, top and bottom, and by the way, that's really all I'm thinking about for at least this initial airfoil, and I'm pretty sure that my final airfoil will be symmetric. Now there are some airplanes that have an unsymmetric airfoil. It's basically an upside down airfoil, but I'm not going to bother with that, at least not on this airplane. And I neglect to mention the 9 means it's a 9% thick airfoil. So in other words, the thickness is 9% of the cord. And then if you need a little bit thicker area, for example, you're going to have a little higher aspect ratio tail and you need a little more thickness near the root, there is the 12% thick airfoil. It's basically the same shape, just a little bit thicker. And just so you can kind of get a comparison of what they all look like, let's compare the 9% and 12%. And let's stick in the tube and fabric airfoil. So you can kind of get an idea of what they look like together and how they differ from each other. So these are the 4 airfoils I'm going to compare. Well, actually, so there's one other airfoil I think we'll throw in here. And this is a version of the airfoil from Harry Riblet in his general aviation series of airfoils. So this is a 30-009, so it has no camber. And just for grins, let's take a look at something. Let's compare it to the 009 NAC airfoil. Now, it's kind of hard to see, but they're almost identical, particularly in the first, 2/3 of the cord. Really, the only difference is back here at the end, near the trailing edge. The Harry Riblet airfoil is a little bit straighter back here, and it kind of looks like it has a cusp, but I don't think it does. I think the NACA airfoil just has a little bit more curve. So that's really the only difference between these. So it'll kind of be interesting when we get to the analysis if we can see a difference in the aerodynamics of these two airfoils. Now I want to point something out on the nose. Let's go up there. Let's get rid of the Harry Riblet and let's put on the tube and fabric and the Minimax airfoil. Then let's zoom in here on the nose. Now something that you'll frequently see in the literature is that an airfoil with a sharp nose, when you start increasing the angle of attack, you will get a separation of the boundary layer at the nose. Now, in a main wing, that's usually not desirable. I mean, you can fly an airplane that has that kind of feature, but it tends to make a sudden loss of lift when you start stalling instead of a gradual one. Now, this purple one, again, is the tube and fabric airfoil. This red one is the Minimax airfoil, and the yellow one is the NACA 0009 airfoil. Now, as you can see, this tube and fabric has a very sharp bend here at the leading edge. And you would really expect it to possibly have that issue of a leading edge stall. Now, the Minimax airfoil actually has a broader, larger radius curve at the very front of the leading edge. But then as you get back, what is that? About 1% back, it is suddenly sharply turning compared to the NACA airfoil. So the NACA airfoil is sharper at the very tip, but then much broader, larger radius a little farther back, about the 1% area. So it'll be interesting when we start to do our analysis how this nose shape is going to be affecting the stall characteristics of the airfoils. Let's go do a little analysis and see what we can learn. This graph we're looking at is coefficient of lift versus angle of attack. This red one is the tube and fabric airfoil, and I had a little bit of trouble to getting the software to come up with a solution for this airfoil. I found out that it does not like to have a rounded trailing edge at all. So I had to make it either open, which is what I end up doing, or pointed. And you can see that this yellow one, which is the NACA 0009 airfoil, kind of follows the typical airfoil shape for coefficient of lift that you would expect. Now this is a symmetrical airfoil, so it's 0 here at 0 angle, and then rises up, has a drop off, and then drops off fairly sharply. And then it's being shown as rising again. I don't know if you can really believe this or not, but it's very possible. But that's a fairly typical coefficient of lift plot shape. Let's look at the Minimax one. So this orange one is the Minimax airfoil, and it has a very interesting characteristic where it does not drop off sharply when it reaches the stall. So here's the stall, maximum coefficient of lift. It drops off a little bit and then begins climbing again. And I actually do believe this, and we'll talk about that more in a moment. And then again, here is the tube and fabric one, and it really doesn't even hardly fall off. It has a little bit of a knee here, but then continues rising. Now both of these airfoils are getting above the 0.8 coefficient of lift, and if you'll remember on the last video when we were working out the surface area for the tail, we wanted to make sure that the coefficient of lift of the tail wasn't required to go above 0.8, and that was to try to make sure that the main wing stalled before the tail did. Now this two-dimensional coefficient of lift certainly makes it above 0.8, so that's at least encouraging. You'll notice that their coefficient of lift, even out here at 20-25 degrees, still doesn't even match the maximum coefficient of the NACA airfoil. So you can take advantage of this higher lift on the NACA airfoil if you would like to reduce the size of your tail. I'm not going to do that. I'm going to stick with the rule of thumb of 0.8. But if you had some reason that you really needed a smaller tail, you would skip using these flat airfoils and go with the airfoil that gives you a nice coefficient of lift, which will let you reduce the size of the tail. I probably wouldn't go up to 1.2, I'd probably go up to about 1 or so. Well, it's kind of interesting looking how the coefficient of lift changes given the angle of attack. In fact, this red plot of the tube and fabric coefficient of lift explains why the tube and fabric horizontal tails have been successfully used for decades. Let's see what happens when we deflect the elevator on the tube and fabric horizontal tail. This dark red line represents that tail with the elevator hinge at 65% of the chord and deflected 15 degrees. With the horizontal stabilizer at a 0 degree angle of attack, we have a coefficient of lift of roughly 1. We have a fairly constant coefficient of lift clear out to almost 12 degrees or so of angle of attack. And then it begins increasing at the same rate down here, but it is higher than when the elevator is not deflected. So when it's deflected, we can easily get our 0.8 or 0.9 coefficient of lift, it looks like. Let's compare the coefficient of lift to coefficient of drag. Well, this is kind of interesting. Let's go down here to kind of the cruise area. So when we're in cruise, we're probably operating around a coefficient lifted down here. So that's showing that the drag on the NACA airfoil is less than the other two airfoils. I'm a little bit surprised that the tube and fabric airfoil has a little bit lower drag than the Minimax airfoil. And I'm not sure you can actually believe this data point here. I really think this probably comes down straight through here. But when you start increasing your angle of attack and increasing your coefficient of lift, that's where this NACA airfoil makes a huge difference in reduced drag. When you're actually maneuvering your airplane, you'll have less drag with the NACA airfoil. Now, given that I want my elevator to be cantilever, and the fact that it has lower drag and can have a higher coefficient of lift, it seems fairly obvious to me that of these three airfoils, the NACA airfoil would be a better choice for the UWS-1 Ultralight airplane. But let's not jump the gun here. Let's compare it to a couple of other airfoils. One will be the 12% thick NACA airfoil. So this was 9%. Let's compare it to the 12. And let's compare it to the Harry Riblet General Aviation U30 a 9% airfoil, and let's see how those compare. Here's the coefficient of lift versus angle of attack. And again, the yellow one is the NACA 0009 airfoil. The blue one is the 12% NACA airfoil. As you can see, it has a higher coefficient of lift. The drop-off after you reach the maximum coefficient of lift is not as sharp as on the 9% airfoil, although we have to be a little bit careful about making that assumption because the software had trouble coming up to a solution along this line. Here was one solution, then it had trouble along here, and it found another solution. So it's probably a little more rounded than this is showing. But I still believe it does have a higher coefficient of lift and a higher angle of attack at that maximum coefficient of lift. So all other things being equal, this 12% airfoil would be superior. And as you can see, the Harry Riblet airfoil is darn near identical to the NACA 9% airfoil. It's got a slightly lower coefficient of lift at the maximum coefficient lift, but it's a little bit higher out here at post-stall angles. Let's take a quick look at the coefficient of drag and see what we can learn. Well, there, except for higher coefficient lifts and thus higher angles of attack, it's pretty close. Now let's take a quick look down here at the cruise condition. So down here at cruise, both the 9% NACA and the Harry Riblet airfoil are almost identical for drag. Now the 12% airfoil has more drag, so not all things are equal. Now if you can tolerate a little more drag, then that 12% airfoil would be a superior performer. But if you're really concerned about drag, then the 9% airfoil would be better. Let's go back to the structural part of building this horizontal tail. What I would like to do is something similar to what was done on the Ultra Cruiser, where there is no spar up in this part of the airfoil, the forward part of the airfoil. The only spar is right back here, right in front of the hinge line for the elevator. I'm showing where the hinge line is that I previously showed for the 15% flap on the tube and fabric horizontal tail. So that would be right here at 65% of the cord. It might be reasonable to go up to about 60% of the cord for the elevator. There's nothing wrong with that. So right in here is where the spar would be. I'm losing some strength in the spar by not having it up here, since the airfoil has thinned out back here where I want to have the spar. Well, maybe there's something we can do to modify the airfoil to have it wider back here. Now we have to be careful not to get too carried away, because this angle back here at the trailing edge has a determining factor on how effective our elevator is. The wider this angle is, the less effective our elevator is going to be. So we don't want to get too carried away. Like we don't necessarily want the widest part to be back here. Let's play around with some options. Here's what I come up with. This pale green line is a NACA 009 airfoil where the maximum thickness has been moved forward to the 22% cord area. And so you can see it's pretty thick right up in here and then begins dropping off to the tail. Now the bright green line is a NACA 0009 45% maximum thickness airfoil. So that's this bright green one, and its maximum thickness is around right in here, and then it starts tailing off. So what I did is I used the spline mechanism, and I matched the forepart of the 25% cord airfoil, and then I also matched the tail part from about 65% back on the 45% maximum thickness cord airfoil. And then I just kind of guessed in between. It's not flat, but there's not a whole lot of curve in between. So it's nearly flat. So the maximum thickness according to the spline is now at 9.77. So it's almost a 10% thick airfoil. But back here at 65% of the cord, where I'm thinking about putting my spar, it's pretty thick, particularly compared to the normal 0009 airfoil. So that should mean I can make my spar a little bit lighter. To help you see the difference here, I've simplified the diagram a little bit. This purple airfoil is our new airfoil, and in the future I'm going to be calling it the UWS-1 H-Tail 009. Here in a moment you'll be hearing me calling it Test 4. By moving forward the thick part of the airfoil, we make this curve here at the front a little bit less sharp, so we're less likely to get separation of the boundary layer at the leading edge. And then here at the back at about the 60-65% chord area where we're going to put our hinge, we got it much thicker so we can make a lighter spar. Well, let's take a look at how well it performs aerodynamically. This is our normal 0009 airfoil. This orange one is the 0009 with the maximum thickness at 40% of the chord. This purple one is the new one that we just came up with. It's being called Test 4. Well, it's got a slightly higher maximum coefficient of lift, a slightly broader maximum coefficient of lift. If this is to be believed down in here, it has a slightly higher coefficient of lift when it starts lifting again. Well, let's check the drag and see how it is on drag. Alright, let's come down to our cruise area. In our cruise area, the drag is pretty darn good. In fact, the only one that's currently beating it is the one where the maximum thickness is at 35% of the chord. So, by golly, at the moment, that's the best airfoil I've seen. Now, it does have worse drag once you start maneuvering up in this area. It's not horrible, but it's not... I would definitely take that if I got less cruise drag. So I can live with that. That looks pretty good. So overall, I'm liking this, if we can believe the program. So at the moment, I'm going to stick with this unless I can think of a better tail to use. I think the airfoil that we've come up with the tail is a pretty good one. Now it's always possible as we get farther in the design and go through some iterations that will change it if we come up with some new characteristics that we decide we need. But now I'm really looking forward to working on the vertical tail. If you haven't done so already, make sure you do a like of the Facebook page for the Ultralight Airplane Workshop. I'll occasionally put little notices in there about status changes or when videos are going to come out or teasers for videos that really don't warrant a video on YouTube. And if you like the channel's Facebook page, you'll get those notices.